This is Stanley Forster recording for physics for IRSC. This is our presentation for Chapter 10, Simple Harmonic Motion and Elasticity. Okay, simple harmonic motion, we're just going to say SHM for abbreviate that for short, is our second example of non-constant acceleration. Our first example was uniform circular motion. Remember, the magnitude always stayed the same, but the direction was constantly changing. Okay. Simple harmonic motion is a type of oscillatory motion where an object moves back and forth about a fixed point. We call these oscillations. And the fixed point is called your equilibrium position. Okay. The motion is called simple because it follows a specific pattern that can be described mathematically very easily. All right, so the idea behind this is very simple. Force law is a restoring force law. This is called Hooke's law. F of x, the x component, is equal to minus kx. Okay, so we can think about this. We take it the equilibrium position. The string is unstretched. We understand there's no force. If we move it to the left, I'm going to imagine me pulling my arm to the left and the mass to the left. As I stretch that spring, the spring is going to pull to the right. So that's what that minus sign is. That shows that wherever I've pulled it in x, its position in x, the force is going to be a restoring force. It's going to draw it back to equilibrium. And notice that as x gets bigger and bigger, that force is going to get bigger and bigger as well. All right? And we can do it the same way. If I go ahead and I bring it back to the equilibrium position and begin to compress it, I begin to move it to the left. Now, and if we have, say, negative course, if that corresponds to the negative side of the coordinate system, I have negative numbers here. Negative times negative is positive. In other words, the force is now positive. The x component of the force is positive. It wants to move the object back to the right. If I were to let go, it would suddenly spring back. All right. Whoops. A little too quickly. Okay, so the displacement in simple harmonic motion, okay, if we were to simply take that spring on a mass and let it go, it would oscillate back and forth. We've seen that. You've seen that with a spring. All right. And it would do so in a regular manner. Okay. And there's two ways of describing that displacement. Its position, x, is equal to some amplitude times cosine theta, where theta can also be described as an angular speed times time. Okay, remember that's from our rotational motion. You remember that an angular displacement, an angular theta, could be described as an angular speed times time, just like a regular displacement could be described as a linear speed times time. Okay, so these two expressions are saying the exact same thing. Okay, the velocity is going to be, your x velocity is minus the tangential velocity times sine theta. And if we convert that tangential velocity to our angular variables, we're going to get negative the amplitude times the angular speed times sine of the angular speed times time. Now remember that this sign here, the argument of this sign is the whole of the angular, gotta see if I can do this. No, it doesn't want to do it. Okay, so angular speed times time, both of those multiplied together go into the sign. The acceleration, the x component of the acceleration is minus your centripetal acceleration times cosine theta, or again, if we plug this into our angular from last chapter, if we plug in our angular variables, okay, translate that, because minus the amplitude times the angular speed squared times cosine omega t. Omega t being the angular speed times time. Okay. Now, when something oscillates back and forth, we call this sinusoidal motion. We have this up and down thing. Now, right here, what they've done is they've taken from one 0 point headed upward through one complete cycle. Now it's going through 0 headed downward, and now back upward. Okay, and they call that one cycle. Now, I prefer personally to take it from one trough to the next or one peak to the next. You do whatever you need to do, but let's keep in mind that A is the amplitude. Okay, so it oscillates from plus A to minus A, and here's a 0. So the full range of motion is 2 times A. All right, the period T is the time it takes to complete one cycle, and the frequency is the number of cycles per second. All right, now think about this. Okay, so if 1 is the time to complete one cycle, the other is cycles per second, These are going to be inverses. The frequency is 1 over the period, 1 over the period, and since we know that the frequency times 2 pi is your angular speed, so we know that 2 pi over the period is your angular speed. Okay, so the frequency of vibration. Now, let's think about this. The stiffer your spring is, the quicker you expect it to vibrate. And the weaker your spring is, the less you would expect it to vibrate. All right. So what we're going to do is we're going to take our displacement. We're going to plug it in here for our Hooke's law. Here's the force. Sum of all the forces equal to minus kx. We're going to take that x and we're going to replace it with our displacement. All right. And then we're going to take our acceleration and we're going to replace that with our expression for the angular acceleration. Notice that we have cosine omega t on both sides, so that gets eliminated almost immediately. And we're equal to minus k times the amplitude is equal to minus m amplitude again, omega squared. Now we work with this a little bit. We're going to eliminate the amplitudes, and we're going to find that the angular speed for our mass and spring system is going to be equal to the square root of k over m. Now that deals very specifically with a mass and spring system. We can get other expressions for the angular frequency for other kinds of oscillatory systems, other things that are even close to simple harmonic motion. Okay, so here's one. Okay, work done by a spring force. All right, so the work done by the spring force comes down to this. It's minus kx squared. Now, if we're going to do the work between two different positions, we need to take an initial and a final position. Okay, 1/2 kx squared minus 1/2 kx squared, where we have two different positions, and that would give us the work done between two different places. Sometimes, very often, your initial position will be 0, so this whole term drops out and is minus kx squared. All right. The elastic potential energy is 1/2 kx squared. Now, this is part of the reason why simple harmonic motion is so important to understand. All right, if we look over here, okay, I'm going to try to bring this in. All right, here's a graph of x squared. You see how that just makes this parabola or bowl shape? Now there's a lot of, if near their equilibrium positions or their turnaround positions, a lot of potential energy functions are going to have this little kind of dip or bowl. Now, sufficiently close, we can approximate that, no matter how complicated it is, sufficiently close. In a lot of cases, we can approximate this with this x squared function, okay? Real close to here, it doesn't have a lot of error between that and, say, x to the 4th. As we get further and further away, it gets worse and worse, okay? But right there near the equilibrium position, we're doing pretty good, okay? So that means for small displacements around the equilibrium position, a lot of systems are going to look like simple harmonic motion. All right. Now, when we get further and further away, those approximations don't work anymore. But if we can figure out the behavior in a set of limited cases, we can kind of extrapolate what the behavior might be in more complex, away from those equilibrium positions. Just use a little deduction. Okay. So before we had that the angular speed was the spring constant divided by the mass. Okay, here's another one. Okay, so this deals with how the physical system is described and all that. But the terms that show up where this angular speed would show up in your equations, sometimes they're like for a simple pendulum would be the square root of the gravitational constant divided by the length of the pendulum. Okay, the longer a pendulum, the slower it swings. And you would think to yourself, if we were higher gravity and the planet were pulling on your pendulum harder, that would actually speed up the swinging. Okay. A physical pendulum is, okay, so a simple pendulum would be like, we consider it a massless spring and a point mass, okay? If we have something that's a little bit larger, like say a ruler is called a physical pendulum. It's not a massless spring. It's more like a rod that has mass all up and down the length. Okay, and in this case, the angular speed would be the square root of the mass times gravity times the length divided by the moment of inertia of whatever that body is. Okay. Okay, so basically you know that for simple harmonic motion, there are formulas for your angular speeds. Okay, simple harmonic motion, object oscillates with constant amplitude. In other words, that energy doesn't go down. Let's go back over here. In other words, if it's not losing any energy and it oscillates out to -8 and over to +8, -8 to +8, -8 to +8, it's not losing any energy. Okay, and that is simple harmonic motion. Now, if we go ahead and introduce friction, in other words, even air friction, you would know that these mass and spring systems, they slow down, okay? Sometimes it's the simple act of heating up the metal in the spring, moving this metal in the spring back and forth, heats it up. Or vibrations in the air. And there's all sorts of ways to lose energy out of a system like this. Okay? These are called damped harmonic motion. And what happens is just that the amplitude dies off over time. Driven harmonic motion. This is where, okay, this is like a child on a swing. So you have a child on a swing and you push, or you can remember pumping, okay? Using your legs and you're pumping. If you do it at just the right spot each time, you can add a little more amplitude each time. In other words, you're adding more energy, you're doing work, and you make that swing even higher, right? Okay, and that is driven harmonic motion. But you have to drive a harmonic oscillator with just the right, well, if you drive it with just the right frequency, you get something called resonance. In other words, that energy gets added to your oscillator each time. Okay, it gets added to the kid on the swing each time. So each time he rises higher and higher and higher. And we can talk about examples of bridges that begin bucking and begin to add so much energy to them that they begin to fall apart. Okay. Now let's talk about some examples of why we would want to know about simple harmonic motion and mass and spring systems. One of the ways that we model atoms and molecules is that the atoms are connected by atomic level springs, okay, and the vibrations in those springs can be described using simple harmonic motion in the equations that we've used so far. Okay, so we're already down to describing matter at the atomic level. Okay, stretching and compressing. This is for your engineers out there. You're going to have to deal with Young's modulus, bulk modulus, and any number of compression and stretching and compression expressions. Okay, and this is you see this delta L here. Okay, that's a position away from your equilibrium. Here's your unstretched length. Here's your stretched length. This is a constant that you have to just look up somewhere in an engineering manual. Okay, but the further we move away from an equilibrium position, the stronger the force gets. All right. So again, this is very much follows Hooke's law. Okay, shear and deformation. Okay, same thing. We're dealing with a departure from some equilibrium position, and this is when the forces are not parallel to each other. Well, examples in the textbook, if you want to send me a note, I can drop off, I can make an example video of how to do one or more of these examples. Textbook gives you lots of examples how to analyze pendulum motion, apply Hooke's law, simple harmonic motion. If you'd like help with any of these, go ahead and drop me a line and I'll make you a tutorial video, and we can go over those in class, in the discussion board, or I can just simply drop you a quick video. Either way, have a good luck with this lecture, this chapter.